Hello there! This video is going to prepare you to look at correlation tables and correlation coefficients and make sense of those results so that you can explain findings in your own words and not have to dig through a results section of a journal article to know what the results were. You'll just be able to look at the table and figure it out. I'll go over some example correlation tables and just thinking about what a correlation tells you about the nature of a relationship, and then we'll end on some practical applications of correlation analysis for reliability and validity. So let's start by looking at all the things for a correlation analysis. In this lecture, I'm really just going to focus on correlations for variables that are assumed to have a linear, not curvilinear relationship, because those are the most commonly used and seen in real research, and they're the easiest to interpret. So, assuming a linear relationship, we're going to look at the direction of correlations and also the strength and significance of correlations. And this should be review for you. The direction of a correlational relationship tells you how the variables are related based on whether scores on the low or high end of one variable's range correspond to the low or high end of the other variable's range. And you can know the direction of a correlation by looking at the sign of the value. So if there's no sign in front of it, it's positive, and you can assume that they tend to change in the same direction. If it's a negative, that means there's a negative correlation, and they tend to change in opposite directions. So again, if X and Y tend to, right, not change, it's not causal, but if they tend to change in the same direction, where higher X's correspond to higher Y's, or lower X's correspond to lower Y's, then the relationship is positive. So for example, food intake and weight, or study time and quiz grades. The more you eat, the more you weigh. The less you eat, the less you weigh. Hopefully, the more you study, the better your grades are, and the less you study, the worse your grades are. However, if X and Y tend to change in opposite directions, where higher X's correspond to lower Y's, or lower X's correspond to higher Y's, then the relationship is negative, and it'll have a negative sign in front of the correlation coefficient. So for example, more cardio exercise, less weight, right? You weigh less. More class absences, lower quiz grades. They're going in the opposite direction, so they have a negative relationship. Here is an example of a positive correlation, looking at an example I mentioned earlier, time studying in hours and quiz grades. Just to make sure you know how these dots work, each dot represents one data point. So, for instance, if we look at this first student, they had a 0 and they had a quiz grade of 65. So that first row corresponds to that dot right there. And you can see the trend in results has an upward direction, right? Such that more time studying is related to higher quiz grades, and less time studying, let's do purple for that, is related to lower quiz grades, right? If you looked at the correlation coefficient for this data, you would see it's very strong and positive. We'll get to strength here in a little bit, but you notice there's no negative here. Same goes with this. This is a positive correlation up here between age and stress, such that the older you get, the more stressful life becomes in this data set. It has an upward direction, positive correlation. Here we see a negative correlation. And again, this is linear stuff, right? So there's no curvilinear nature. We're only focused on linear relationships. And here we're looking at how many hours of cardio do you tend to do per week and your percent body fat. Yet again, if we look at this first person in our data set, they had a 0 and a 22. Here they are. All right, just to make sure you know how the dots correspond to the numbers. And here we see a downward slope, right? The dots are going in a downward direction. And even if we didn't have this picture, which typically journal articles don't give you the scatter plot, but it's nice to kind of visualize what the data looks like based on the number that they usually give you, which is the correlation coefficient. And you'll see here we have a negative. So that tells us we have a negative inverse relationship. Same thing up here, right? We have a downward slope such that those who are older tend to party less, And those who are younger tend to party more. And we see that negative sign in front of our correlation. Now let's pivot from looking at the sign of the correlation, positive or really nothing, or negative, to looking at the actual numeric value of the correlation. So strength of the correlation tells you how consistent the relationship is among variables and really how linear the relationship, right? How close those dots fit that line or, cluster together. And again, strength is denoted by the numerical value of the correlation coefficient, and it ranges from 0, no relationship, to 1, perfect linear relationship, or I'm going to add this, -1, because really we're really looking just at the number, not the sign. But I know some students may look at a negative correlation and think it's weak, but it's not. So I'm just going to put that there. Okay? So for a strong relationship, closer to 1 or -1, every time x increases by 1 point, y changes by a consistent amount across all study participants if you had a correlation of 1. That would be like a perfect linear relationship. Again, each 1 point increase in x would result or be related to the exact same change in y for every single person in the data set if you had a correlation of 1 or -1. So for instance, you could say each hour of study time, each additional hour of study time consistently yielded 5 more quiz points. That would be a correlation of 1 if that's what the data looked like. Or each additional class absence consistently yielded 5 less quiz points, right? So for each additional absence people had, everybody in the sample had 5 point fewer quiz points for each additional absence. And that would be a perfect strong correlation of -1. A weak relationship is when you have less consistency. Your data points are kind of spread all over the place in the scatter diagram, and there's not a consistent change in y for every increase or decrease in x in your data. So, for instance, every time x increases by 1 point, y changes by some variable amount across all study participants. So maybe each additional hour of study time yields a small point increase for some in the quiz grades, a large point increase for others, and maybe even a point decrease in some, right? That would be a weaker, less consistent relationship. And you can evaluate the size of correlations, we'll get to effect size here in a little while, based on looking at R and seeing how close it is to these values. And if it's close to 0.10, it's weak. If it's close to 0.30, it's moderate. If it's closer to 0.50, it's strong. And anything 0.70 and above is very strong. And you can kind of graph these out, right? These would be like 0.10 be here, and then 0.70 would be here, right? And then negative 0.10 here, negative 0.70 here. You can see it can be strong, negative, or positive. So let's look at an example of a perfect linear correlation where it equals 1. Here you notice, and I've got these listed in numeric order to make it easier, for each additional 500 calories, weight is going up 50 pounds. So that would be a perfect linear positive 1 correlation. It's rare in reality, but there it is. Here we can see more strong correlations that are more realistic. So here we have a consistent increase in age as stress goes, or increase in stress as age is going up. Those who are older tend to party less, right? We've seen these before, and these were all strong. Those who study more tend to have higher quiz grades. Those who do more exercise tend to have less body fat. But it's a really consistent trend in results, right? You see that they're kind of, the dots are fitting a line pretty closely. And when we get to regression, you'll see that the stronger a correlation is, the more effective your regression equation is at predicting outcomes because there's less variance in your predictions. Now let's take a look at a correlation with moderate strength. A moderate strength correlation, if you drew lines around it, it's kind of like a football shape, almost, or a lemon if you're not into sports. And you can see that dots are spread out. There is variability, right? When we look at how many people children have based on the number of siblings they had growing up. But we can clearly see there's an upward trend here, right? We can tell the direction of it. So if your data points are spread out, but you can tell the direction, you've got a moderate correlation. And here you see that with the value. It's close to 0.30, so it's a moderate correlation. And it's positive, right? Because it's going upward. Now here's an example of a weak correlation. Something around that 0.10 mark or lower, right? That you see here. Data are so spread out that you really can't tell the direction of the relationship at all. It's kind of like a shotgun blast went off. And if you draw a lot, or you draw your data points, it's going to be kind of a circle. And that just means there's not really a consistent relationship between the scores people got in anatomy and physiology and the number of stations they pass on the OSCE. Here's another example of a weak correlation between number of siblings and number of children. And this is actually based on some real data. And you can see there's no relationship there, right? Weak correlation. It's just spread out. You can't even tell the direction. Now let's shift our focus to, instead of visualizing the correlations, thinking about how reliable correlations are based on p-values. And I want you to keep in mind that just because a correlation is significant, has a low p-value, as we'll get to in a minute, doesn't mean it's strong. So the p-value is really the probability of error. The probability, p for probability, that whatever you observe, whatever trend you found, is really just a fluke and not due to a true relationship between the variables. So usually in correlation tables, you'll see a star to indicate p less than 0.05. And that means if p is less than 0.05, there's less than a 5% chance that the observed relationship that you're looking at is due to error. If a p is less than 0.05, that means your findings are significant, and it means that your findings are reliable, and that you can be confident that what you observed in your sample would probably be observed in the population because there's a real relationship between those variables. If you take p and you multiply it by 100 to get the percent, that really just tells you the chance that sampling error caused observed results. And since we don't want error to be the cause of our results, we love those low p-values. And in behavioral research, usually our standard is 0.05. And that 0.05 rule is a bit arbitrary, but it has been the agreed upon cutoff for the probability of error to call findings significant for a long time. Historically, it's been really difficult to publish research if you don't have that sweet p less than 0.05 in your results. But currently there's a debate about this cutoff and a big push to report p-values for all the results without much concern for significance. That will help people focus more on the magnitude of differences or effect size, and publish results that aren't necessarily meeting that cutoff but are still really worthy of people knowing about. Your confidence level in results also depends on more than that p-value. You really have to consider the quality of measurement, the quality of manipulation if you're doing more experimental types of research, and how representative your sample is. So having that cutoff of p equals 0.05 is a little bit, or p less than 0.05 is a little bit dangerous in research, and we're kind of moving away from it. But the p-value, regardless, will tell you how likely it is that your results are due to error, or just random differences that had nothing to do with your variables being related. As researchers start to move away from that hard focus on p less than 0.05, we're starting to focus a lot more on effect size. And effect size is a measure of practical significance. So even if a finding is statistically significant or reliable, practically speaking, that doesn't necessarily mean that the relationship between the variables was strong or even moderate. In fact, it's easy to get weak and statistically significant correlations with large samples. So with correlations, it's pretty easy to determine the relative size of the effect because you can just look at the correlation coefficient and evaluate the strength. But effect size is especially important in experimental research where you've manipulated something and then you're measuring the difference in the dependent variable, and you're not using correlations to do that. You're using t-tests or ANOVAs or something else. You can still compute an R-squared, and it will tell you the relative impact of the effect that your independent variable had on your dependent variable, regardless of whether it's significant or not. And that can be really useful too. So there's lots of measures of effect size, but my favorite is R-squared because it can be interpreted with a pi. So R-squared tells you how much of the variability, or all the differences among the scores, values, or data points, whatever you want to call them, so how much of the variability in those scores for the dependent variable are related to differences in the independent variable, or how much of the dependent variable pi is due to the independent variable or quasi-independent variable in correlational research. So for example, let's say that your X variable, your quasi-independent variable, or maybe even an independent variable if you did if you manipulated this variable, would be work group diversity. So that's our quasi-independent variable. And that, in this case, since we're doing a correlational type of study, we're going to ask people their perceived ethnic and gender representation in their work group on a scale from 1, gross underrepresentation of minorities, to 4, equal representation, to 7, overrepresentation of minorities. So we're looking at work group diversity as our independent variable. And then our dependent variable is work group creativity. I'm sorry, quasi-independent variable is work group diversity. Now our dependent variable is work group creativity. And we're going to operationalize that by looking at the number of unique solutions to an organizational problem. And we're wanting to see if they can tell us how to incentivize high performance among employees in the department for under $1,000. And we'll just count how many good solutions they come up with, and that's our measure of our dependent variable of work group creativity. Let's say in this study, we got an R-squared of 0.28. Well, that tells me that 28% of all those differences within the measurements of creativity, with those scores or data points for creativity, 28% of those differences in creativity are explained by current levels of perceived work group diversity. And that would be a large effect. Because if we can predict that much variability in our dependent variable with just one variable, we're pretty excited. Because there's a whole host of factors that go into predicting work group creativity. But if we're able to nail down that big of a chunk of the differences in creativity with diversity, we're onto something. So now we're back to looking at a real journal article, and I'm going to show you how to look at the correlations that are provided there and make sense of it. Remember, you can go through all of these steps to make sense of a journal article, especially if you're doing something like an annotated bibliography or you're trying to summarize research to justify a hypothesis. But here, we're just going to focus on figuring out the key findings for correlation results in a correlation table. So we are looking at the same article that we looked at before, the Why Me Frog Pond Effect, Relative Deprivation and Individual Outcomes in the Face of Budget Cuts. And you are welcome to go ahead and pause and take a moment to read the abstract to get an overview of the journal article and the research that we conducted. Now I want to show you a correlation table from the article just to show you how to read correlation tables in practice. So we already looked at the means and standard deviations in the previous video. So here I'm just going to kind of focus on this section to the right of this line. So let's say that I wanted to find the correlation between two variables. The first thing I need to do is find the intersection of those two variables in my table. And so you notice that we have all the variables listed here. And then here we just have numbers. But keep in mind that 1 is personal impact of budget cuts, 2 is job satisfaction, 3 is effective commitment or emotional attachment to the university they worked at, 4 is psychological contract breach or perceived breaking of promises that they felt they were made, 5 is turnover intentions or how much they want to quit, and 6 is the departmental impact of budget cuts. You'll notice there's no correlations here, and that's because we measured departmental impact from department chairs, and we measured all these other variables from staff and employees, so we only had correlations for them. So let's say that I wanted to look at the relationship between job satisfaction and turnover intentions. And my hypothesis is that those who are more satisfied will tend to have fewer turnover intentions, right? They don't want to quit. So I'm expecting a negative relationship. Let's see if that's what we got. So we're looking at variable 2, job satisfaction, and variable 5, turnover intentions. You'll notice that we can't do that here, right? I can't go to the second row and look here. That's not there. And that's just because those correlations would be redundant with the ones below. So usually you'll see an empty space there. So to look at this, I need to go down to the variable that's further down, turnover intentions, and then go over and find column 2 that represents job satisfaction. And right here is my correlation, right? And so as I suspected, it's a negative correlation. And in this table, all of the findings had p less than 0.01. So that tells me that not only was p less than 0.05 significant, right? P was less than 0.01, which means that there was less than a 1% chance that the relationships that we looked at here were simply due to sampling error or random variation or noise in our data and not due to a real relationship. So that's why all those correlations are statistically significant. Now let's look at the results. If you're looking at this, right, and you're like, I can't figure this out, it's really hard for me, I still don't understand direction, that's okay. The article will give you a summary of the results. So in our article, you can see here when we looked at the personal impact of budget cuts and how it was related to outcomes, there's an explanation of it there. But it helps to know what negatively associated means, right? So just try to keep in mind, negative is an inverse relationship. Higher for one is related to lower of the other. And then positive is they go in the same direction. Higher is related to higher and lower is related to lower. But see there, even if that table was scary, you would get the results explained to you. Even if you forgot what was significant and what wasn't, there will be results in there explained in writing. So it's also important to practice explaining findings in simple language. So see if you can try to explain the overall trends and results for that personal impact of budget cuts. So go ahead and pause it and see if you can explain overall, like overall employees who experienced stronger or more personal impacts of budget cuts tended to have what? See if you can explain it in your own words. So I highlighted what you need to focus on here. Go ahead and ignore this first value because we'll talk about it later. All right. So here's my example, and you may have something slightly different, but employees who experienced greater individual impacts of budget cuts, right, higher scores on budget cuts, tended to have less job satisfaction, lower emotional attachment to the organization. So I kind of took effective commitment and put it into simple language. But notice we're saying less and lower, more of budget cuts, less and lower job satisfaction and effective commitment because these are negative. But then the positive correlations, right? Those who experienced greater individual impacts of budget cuts tended to feel that the organization broke more promises. So that's a simple way to say there was more psychological contract breach and they wanted to quit their jobs. So a less fancy way of saying higher turnover intentions. We are now going to switch our focus to reliability and validity and how correlational research can help with that. And you will see an example of the Cronbach's alpha, the little weird correlation coefficients that we ignored here in a bit. So in addition to being able to examine the relationships between variables of interests, correlational research can also do a lot of other things, like examining the reliability of surveys. So looking at the internal consistency of multi-item survey scales with questions designed to tap into the same construct. And that uses Cronbach's alpha. And really, we have a general standard that if you have a Cronbach's alpha of at least 0.70 or above, you have consistent responses among people. So that people who had a high score on one question that's designed to measure this construct tended to have similarly high scores on the other questions measuring the same construct. And conversely, if you get a high Cronbach's alpha, that means that also people who had a low score on one question measuring that construct tended to have similarly low scores on the other questions measuring that construct. So that's what internal consistency with Cronbach's alpha tells you. The closer that value is to 1, the more consistent people tended to respond on all those questions that were supposed to be measuring the same thing. Then you have test, retest, and multiple forms reliability. And this can use a repeated measures correlation. So you can see if people's scores on a test or a survey that they took on Monday are highly correlated with their scores on the same test taken on Friday, for instance. And if they have similar responses across time, then they would have test-retest reliability. Or you could look at, for alternate forms, if people complete 2 different versions of a test or survey that's supposed to measure the same construct, their scores better have a strong positive correlation so they can conclude that there's alternate forms reliability. Correlation can also be used to examine the validity of surveys. So you can look at criterion validity. You can see if the predictor, if your survey, your IV, is related to some sort of behavioral outcome to look at criterion validity. So for instance, you could make sure that there's a strong correlation between turnover intentions that you measure with a survey and them actually quitting their job 6 months later, right? Is it predicting a real behavior? You can also use correlation to measure convergent validity. So that's where you look to see if the measure for your construct is related to other tried and true measures of similar constructs. So you could have a survey measure of self-esteem that you're developing, and if it actually measures self-esteem, it should have a strong positive correlation with a measure of confidence, because that's something that's very similar to what you're measuring in your construct before. So you want to see that self-esteem is related to confidence because past research suggests they are. So your measure of self-esteem should be related to a tried and true measure of confidence. Then discriminant validity is kind of the opposite of convergent validity. It's where you want to make sure that your measure for your construct is not related to tried and true measures for different constructs. So for instance, a survey measure of self-esteem should have a weak correlation with locus of control, which is designed to measure perceived control over their lives. And this is just there to make sure that you're not going to have everything be related on a survey scale just because they're all in the same survey. So the discriminant validity really helps with that. Here is our friendly correlation table yet again, but now this time we are going to focus on Cronbach's alpha, or our reliability estimates, our coefficient alpha. So how reliable were these measures that were designed to tap into the same construct? So if we look here, we can see that all of the measures except for turnover intentions, which is variable 5, so right here, all of those measures but turnover intentions have that acceptable Cronbach's alpha of greater than 0.70. Psychological contract breach, if we look here, variable 4, overall it has the highest Cronbach's alpha. So that means that the measure for psychological contract breach had the most consistent responses within each person. Interestingly, psychological contract breach had the highest standard deviation though. So if you look, had the highest standard deviation, but also the best alpha. So although the responses, each person tended to respond in the same way to the items, like within each person, higher standard deviation means that it had the most inconsistent responses between people. So within each person, people who rated it high tended to rate all the items high. People who rated it low tend to rate all the items low. But if you compare between people, there was a lot of differences in how much people had psychological contract breach or how many promises they felt that had been broken. So again, the survey questions or items designed to measure psychological contract breach all appeared to measure the same construct because it had the Cronbach's alpha that was high. But people tended to disagree about the level of psychological contract breach they were experiencing based on that standard deviation that shows different people in the sample tended to have inconsistent overall scores. If you want to read the article, here is the reference, and I hope that you found this to be really useful, and I hope that understanding how to look at correlation tables and make sense of results and what Cronbach's alpha means will really help you save time when you're reading journal articles on your own.